Welcome to class meeting 9 of EECE574, the graduate level probability and random processes. As always, we have announcements about homework and handouts. There is no abnormality, so I will skip that. About my repeated messages, let me emphasize this part. So whenever you have a new idea of concepts, what do? You have to use your brain. Your brain, as your computer, has some storage device or parts. So you search for what is something similar to what you just have known new. So you compare. You compare that what is new and what you have, everything you have, and try to find the commonality or similarity and difference. Then, interestingly, as much as you learn, you can compress the knowledge stored to be stored in your brain. Sometimes you find some commonality nobody has discovered, which can be translated into a new thesis, new paper, new research results. So one thing you remember is that memorizing something is very important. I sometimes hate those people who say that memorizing in learning is not important. It's very important. It's the basis of every learning. However, when you memorize something, you have to have a well-structured memory. So try to keep your brain well organized. That is very important. You already experienced that your closet sometimes is very crowded. However, if you sort them out, then sometimes you can find new vacancy. The same thing happens in your learning. So never forget. Try to find commonalities, similarities, and difference. In order to do that, you have to remember this kind of doctrine, but also you have to be more careful in drinking alcoholic beverages, because in your stage of age, you are prone to drink alcoholic beverage your friends. It really damages your memory. So try to avoid that. There are many non-alcoholic beers and very low alcoholic soju and other distilled liquors. So try to have that instead of very strong, very high intensity alcoholic beverage. Very, very important. Got it? Because, for example, you learned something today in this classroom and you drink some beer tonight, then something you learned, which was stored in a short-term memory, has no time to be moved to your long-term memory. Alcoholic beverage prevents that kind of transition. So your entire day is lost by simply drinking a beer, okay? Of course, I exaggerated, but remember that. Anyway, also, when you have some conflicting opinions, try to find pros and cons, but never forget that sometimes the pros can become cons. Cons can become pros given new technology in our electrical engineering. You can easily find that kind of example. Sometimes people abandon the idea of what? Electric vehicle. Actually, when people first had the automobile, some people tried to use steam engine for the automobile. Some other people try to use combustion engine for automobile. The other people try to use electric vehicle because, as you remember, even before the invent of combustion engine, there was battery. So if you search for some pictures then you can discover very old 1890 something or 19 or some years photo showing first electric vehicle. Probably at that time, people said that, okay, battery cannot store much energy. We need this much energy. Steam engine is too heavy, so we can't do that. So at that time, probably the pros was on the combustion engine. Now what's going on? As the technology evolves, the energy density in a battery increased dramatically. Now we can see a lot of electric vehicles. If you go back to 100 years ago and claim that electric vehicle will prevail, at least in stock market, as you know, Tesla, nobody will believe. They say that invest in Ford, right? But what about the stock price of Ford automobiles? Probably Tesla is much higher. Anyway, so never forget this. Anyway, fortunately, now we have finished the chapter 3 of our undergraduate reference book. Now we move to chapter 4, entitled Multiple Random Variables. Fortunately, there were not much to correct or clarify, so I will just simply list up what we learned in the last class meeting, which was actually recorded version dictated along by myself, but let's do that. So we reviewed how to obtain the CDF of the output of a deterministic mapping. So let me draw. So here goes some deterministic function and input output. So you have a system, a deterministic system in terms of our electrical engineers terminology. And sometimes your input may be a scalar with uncertainty. But then what is the output? Output is also, in this case, if G is a mapping from R to R, R into R, then Y is what? A random variable, especially real-valued random variable. About that, I decomposed this part. So we have a source, and we decompose this into two blocks and combined these two blocks together and easily showed that output is a random variable by using our measure-theoretic definition of the random variable. Got it? Anyway, so we wanted to fully describe the output, and since output is a random variable, CDF is one of the choice. So we start from CDF. And as you've seen in the recorded class meeting, we started from the definition of CDF. What is CDF of Y? Probability of event that random variable realized is less than or equal to some lowercase y. And then we change this event in the probability measure into what? Some other event, equivalent event, perfectly equivalent event, but now in terms of random variable x. Then we can use the probability measure of random variable x, or sometimes we can use the probability measure of the underlying probability space. Then we can find the CDF. If we want to find the PDF, what do? We differentiate the CDF. That is the principle. And this approach is called the direct approach or direct method. And we've seen some examples. First, when G is an affine function. What's the difference between linear and affine? Affine has possibly non-zero constant added. Anyway, so we exercise with AX plus B, where the case with A equals 0 gives us headache, but in that case, simply Y equals B always, which means that our PDF of Y, is direct delta function. By the way, I had a beer last night, so I'm not, my condition is not 100%. Anyway, by the way, the natural choice after examining affine would be squaring and then quadratic, right? However, we also generalized a affine function into a monotone function because if A is positive, y equals ax plus b is a very special monotone increasing function. If A is negative, this affine function is a very special case of monotone decreasing case. So we kind of combined these two to reduce, compress our knowledge. And then here goes Jacobi's method, and which is, as I explained in the video, can be much easily understood by using the idea of histogram. That's why I really emphasize scatter plot, histogram, histogram, instead of, hey, here goes Jacobi's function, and then in chapter 4, Jacobi's determinants, Jacobian determinant matrix. I don't say that. I would rather say that think about the scatter plot and then try to construct a histogram, then you can easily understand Jacobi's method. While I was explaining this, I later found that I needed more explanation. So let me do that, okay? So suppose you have a mapping rule, g of x, shown in that way. And now, suppose you want to find the density of y at some y0. So your objective is to find something like this, okay? Density of the output evaluated at y0. According to my explanation, what do? You kind of consider a small bin here. Because anyway, this density is what? This density function is the limit of the normalized histogram evaluated at y0. So before normalization, you have a histogram, normalized histogram, right? So you have a bin here, and then this bin has, in this figure, 4 corresponding bins, right? So this is the first bin, sorry, 5, 2, 3, 4, and here 5, right? So what you can easily understand is that in order to observe some realization in this bin of y, you need to generate x. You have to have some x generated either one of these 5 bins, right? So we can easily guess that this density function must be some, possibly, weighted sum of what? Density of x evaluated at these values. Let me write it this way. This is x of 0, 1, but since we need y0, sometimes I would say that the representative value of this interval as x, y0, 1. Got it? So you somehow find the inverse of y0. So if you want, you can say that, okay, if G inverse exists, G inverse y0. The problem is that G is not monotone, so you may have multiple values. So let me use index 1 here. Got it? And then this value may become x2, y0, and using more friendly definition of inverse function, we may say that G inverse of y0 subscript 2, something like. So you have G inverse some I of y0, and this number of terms depends on y0. So this index should be very complicated, but I will just skip that. Then what would be the weighting coefficient? And that's interesting, right? And you just need to remember this. Okay, let's go back to this case. What was that? We've seen absolute value of A in the denominator. You remember that? In this case, what? Density of Y equals simply density of X, G inverse Y, and divide by A, right? And what is A? A is the first order derivative of G. So this coefficient must be something related to, Y. Absolute value. Got it? So that is the idea. So you remember the simplest affine case, you memorize, you really need that. And it's very, very convenient, okay? Or sometimes some of my friends, when I was a graduate student, just memorize the scaling device case. They believe that this is much easier. But anyway, it doesn't matter. Anyway, so does it make sense? Of course. So if you want to memorize that, it really makes sense. And you can even write it this way. What is this? This is dy dx, because y equals gx, right? And evaluated at G inverse y0 I. And be careful, you need absolute value. Got it? As you've seen here. One of the reasons why we have absolute value is that suppose we have -1. In that case, this is straight line. But what is important is the corresponding bin, not the order of the two endpoints. Got it? Anyway, so let me be quick. So that is Jacobi's method. And this method will be extended to multiple random variables case, as you will see this week. The final topic was computer generation of a random variable. And I told you that this is very, very important because if you look up some old books, those were popular when I was your age, they were entitled as numerical recipes in something. And that place of something, there were different computer languages. So if you search in our poster library, probably they have all numerical recipes and in and enter, then you will see numerical recipes in Fortran, numerical recipes in COBOL, numerical recipes in C, and I don't know, probably numerical recipes in Python you may find. I have numerical recipes in C in my bookshelf because at that time C was very popular. And one of the page shows how to generate a uniform random variable. 0, 1 uniform random variable. And there were comments saying that people used this algorithm and generate a lot of research papers for simulation. And then suddenly some clever guy found that that really cannot generate uniform random variable. It is sequentially used. It is so many of the old results could be should be abandoned. Some comments like that. So anyway, computer scientists and engineers try to find a method to generate a uniform random variable. Sometimes it can generate all 0. Sometimes it can generate all 1, but that doesn't matter in most of cases. So you may say that uniform 0, 1 excludes two endpoints. That is sometimes much easier to understand. And then the question is this. Once we have a pseudo random number generator, that practically in engineering sense, really generates IID, uniform random variable, from 0 to 1, what kind of deterministic function, as we've seen here, what kind of deterministic function G should be used to obtain a desirable probability distribution or desirable random variable? And the idea was quite interesting. So if you want to generate some desired CDF, so let's say that you have some desirable CDF, and let's call it F, capital F sub X. Then here, G must be what? G must be F sub X inverse of course, U. Okay, this is function of U. Okay, and then you may say that the output here follows the distribution of your targeted CDF. Here, you should be careful because this notation itself assumes that the CDF is strictly increasing. CDF is always increasing, but not necessarily strictly increasing. So that notation actually does not mean the inverse. It's rather than the percentile function of X. What does that mean? If you have some flat area and try to reflect that with respect to the straight line y equals x, then you have a vertical line. And also, if you have discontinuity, then you have no points. And you remove that vertical line and you connect the discontinuity, then you have a so-called the percentile function. And use the percentile function, then you can always get the desirable distribution. Here goes some straightforward idea that you put here the CDF again, then what? Let's say that the output is V, and V also follows the uniform 0, 1. But be careful. Here, if X is discrete, then what happens? Let's see. If X is discrete, for example, 0, 1, with 1 minus P and P, then your CDF is what? Here, you have sudden jump and jump, right? Now, what happens? Can you get the uniform? You can't, right? It is because here, actually, the assumption is wrong. Inverse function does not exist. So you can't say that when X has jump discontinuity in the CDF. This is true only when real inverse of CDF exists. Got it? So that's what I wanted to say at the end of last class. Of course, I talked about uniqueness, and you should be careful. Here, you can just simply change it like 1 minus U, then what happens? V is not U, right? Even if these are inverse of CDF and CDF of X. Got it? So uniqueness is not guaranteed. That is also very important. Okay, today and on Thursday, we are going to cover chapter 4 very quickly because many of the ideas are simple extensions from 1 dimension to 2, 3, 4, n dimensions. Okay? So we are going to define the random vector, And there are, of course, undergraduate and graduate versions. And I will ask how to fully characterize a random vector. And your answer would be almost the same. There are two versions, undergraduate version and graduate version. And there comes the idea of joint CDF, PDF, PMF, and also a new idea of marginalization. This is rather used in electrical engineering students' textbook. However, since the machine learning is very popular and marginalization, the term is quite often used, I have to introduce that idea. Anyway, and then we will repeat what we've seen in the probability chapter. We are going to talk about conditional now, CDF, PDF, PMF, when we have more than one random variables. And especially, we are going to do point conditioning. About point conditioning, we've just seen so far something very straightforward, something like, okay, what is the density of function of x when x equals a? Then we had something like this, right? For example, x is a standard Gaussian, and you've seen a equals 0. And my question is, what is the conditional density of x given x equals a? Then delta function, right? Now, this idea would be generalized because here in this, on the right side of the conditioning bar, now you can have some point conditioning in terms of, for example, the other random variable y. That is very important. And then we will revisit our chain rule. We will revisit our total probability theorem, Bayes theorem, and also the idea of independence. And so everything is repeated. That's why in the beginning of today's lecture, I said that you have to search for something similar in your brain because we have that in our brain already. I hope you didn't drink too much last night, okay? Okay, here goes the chapter. The first thing is this one. So suppose we have a random experiment. So this is a kind of undergraduate version. So this is a random experiment with, for example, two real numbers generated and they have uncertainty. Let's call the first one as x1 and let's call the second one is x2. Then we can put these two together and define a vector having these two components or sometimes entries or sometimes members. Then what is this? What would be the appropriate name of this one? According to our definition of random variable, it's very appropriate to call that as a random vector because we now have a vector, in this case, of 2 dimension or length 2 vector with uncertainty, right? So we can call this a random vector. However, many mathematicians and statisticians call this differently. They call this a multivariate random variable. They still say that this is nothing but a variable because in their mind, vector is a special variable. But engineers rarely do that. They just say that it's a vector. So I prefer calling this entity a random vector. So I will rarely say that it's a multivariate random variable. Anyway, so this is our undergraduate version, but now what do we need for our graduate version? In our graduate version, which means that we have what? Underlying probability measure, space that characterizes a random experiment. So we have sample space, event space, and probability measure. And then what? if we have a single random variable, what? Its output is mapped by x1, right? And we have the output x1. What if we have x1 and x2? It's very natural to make a tab and put here a function in parallel. So interestingly, two different, possibly the same, two measurable functions that are fed by the same value s, which is the outcome of the random experiment, generates two mapped values in the real or sometimes extended real line. So x1 is what? A mapping from the sample space to R or R bar. x2 is another function that maps the sample space into R or R bar, okay? Depending on whether you need a point mass at plus minus infinity. If you don't need that, then your core domain of the two measurable functions should be ordinarily the real line. Got it? So this is the idea. And what you did in your undergraduate was enclosing these parallel interconnected systems to the underlying probability space into a single block. Okay, got it? So this point of view is very important, especially, this is the most important part, especially you have more than 2, more than 3, more than 4, and eventually in the next chapter, when you have a sequence of random variables, in that case, you have a countably infinite branches with subscript n, and you have a function for every natural number n. In the case, you have countably infinite measurable functions fed by the same outcome s, and you have a random sequence. Sometimes you have not only in this direction, you have the other direction. So you have x sub 0 of s, x sub -1, -2, negative. That is in engineering called a discrete time if the subscript means time, a discrete time random process. Got it? And what about a continuous time random process? In that case, you have uncountably infinite branches. That is the idea. And you will see in the last half, I hope, last half part of this course. I really hope I can finish this review before the midterm. Anyway, so you get the idea and the big picture. This is one of the most important picture. Okay? For random variable, you would have said that, okay, it's just measure-theoretic point of view. That's it. No, it's very useful when you try to understand the random vector and a random sequence and the discrete time random process and eventually a continuous time random process. Of course, what you learned in your undergraduate probability is still important. So probably you would say that, okay, I was not taught in that way when I was an undergraduate student, but I could do almost everything, especially with 2 random variables and some finite number of random variables, right? At that time, as I've shown you in the outline or preview of this today's meeting, the joint CDF, joint PDF, joint PMF were enough. And that's still true. But you have to have one more thing in your toolbox. That is the measure-theoretic understanding. Some very complicated ideas in probability and random processes, it really requires this point of view, this new tool in understanding a random vector, random variable, random processes. Got it? So this is one of the most important figure in this course. Okay, now let's go back to our friendly ideas. So suppose you have two random variables generated by a single random experiment. Got it? And what about full description or full characterization of this thing? How can you do that? And whenever I ask something like this, how can you fully characterize random something? You have to go back to this one and try to generate some outcome and try to find the outputs of these two mappings. Then what happens? You have a two-dimensional plane and a point. So here goes, let's say, x1 axis, and here goes the x2 axis. Now, suppose you generate some s. We don't know how it is mapped, but you have a single point, right? Now you have a point. Let me call it P1. Now you independently generate the second outcome, and possibly you have some other point. P2. You repeatedly do it until you are satisfied. So many realizations. What is the name of this one? This is two-dimensional scatter plot. And as far as two-dimensional real random variable is concerned, this contains almost every information about the random vector. Now, what we need to do is to remember what we learned in one-dimensional case and try to generalize that into 2 dimensions and 3 dimensions and n dimensions. Got it? So what do you do? First thing was to have a scatter plot, and the second thing was to have a histogram, right? Now you have 2-dimensional scatter plot. So what you need to do is to plot a 2-dimensional histogram. What do you do to plot that? You divide the x1 axis into bins, and you divide the x2 axis into bins. Of course, this is not the only way. You have some irregular partitioning of the entire R to the 2 space. By the way, here R to the 2 is the set of points such that these two numbers are real. Got it? Of course, sometimes R to the 2 is used to denote the 2-dimensional Euclidean space, which means that not only this set of points, but also we need the metrics such as distance. We need the notion of orthogonality, which requires the notion of inner product, something like that. But anyway, so at this point, you have R to the 2 plane, 2-dimensional real plane, and a scatter plot, and you partition this set into countably, possibly infinite numbers, or countably finite numbers. Sometimes what you do is simple. What you do is that you divide the entire plane into these 16 areas. By the way, these 4 includes infinite plane, and these 8 also includes the plus minus infinity. Only these 4 are finite. Okay. Sometimes your bin, even though bin means something finite, bin could be infinite. Got it? Anyway, so what you do is that you partition that and count the number of realizations. In order to normalize that, what we usually do is that we divide it by the total number of realization. In that case, if we sum up the height in each bin, we always have 1, right? But sometimes we further normalize by using the area of this one. Of course, in this case, it's very hard. But if there is nothing realized, then it's okay. We can ignore that. In that case, we have something interesting. We have some piecewise constant function, two-dimensional function. And if you integrate that over the entire R to the 2, then you have 1. Now, what you do is that you generate more and more realizations, and you shrink the area of each bin with counts infinitesimally small. Then you have something very possibly very smooth and still integrates to the unity. That is the idea of what? The two-dimensional probability density function. So the idea, the procedure is this one. You consider the 2D scatter plot, then 2D histogram, you normalize, you generate a lot and reduce the bin size, and you eventually have two-dimensional, or sometimes called joint, because you have two random variables. In Korean, 결합 확률 밀도 함수, joint probability density function. Got it? And that is why this approach is very appealing and very intuitive. So be careful. Whenever you whenever you read some very difficult, highly mathematical paper, research paper, never fooled by the order of presentation in that paper. In many cases, the researcher who wrote this paper, the authors, started from possibly a complicated problem that is presented. However, they divided the problem into smaller ones and also applied the simplification. And sometimes they had a bold guess of the solution, and they proved somehow, but found that that approach is shabby. So they use esoteric mathematics to prove in a better way, and then suddenly, voila, you have that paper. So never feel this way. Okay, oh, very difficult math. How they get the end result? Actually, they got the result first and then justified using math. Of course, if it is true, you have a very beautiful math. You can always find. Even I also did that for some of my papers. And when I first have given that paper to already graduated, some of my graduate students, they said that, professor, it looks too much compared to my math skill. I said, no. My skill was no better than your current skill, okay? After I got the idea, I learned the math, and I found some research papers related to that skill, that tool, and then I justified and reordered the presentation to make it look beautiful and esoteric. Esoteric means kind of elegant in academics. Sometimes I may say the pedantic. You may don't know that word, but that is vocabulary 22,000 word. But pedantic means 학자연하는. Got it? 학자인 척하는. Okay. Anyway, you can make it later. So never fooled by the research papers. That looks very difficult. Anyway, so we are now at this 2D PDF. Then why do we need this joint PMF and joint CDF? Sorry, this should be CDF. Okay. It should be CDF. Here goes the idea. Okay. This is more like our undergraduate approach, right? What would be the measure-theoretic counterpart? So we start from measure-theoretic one, starts from our probability space that describes the random experiment and two measurable functions. And what? And what? As we've done for a single random variable, from these three, we can find the induced probability space. Now, its sample space is R to the 2. Its event space is the two-dimensional Borel sigma algebra, which is a 2D extension of the Borel sigma field. And then we have our probability measure, which has very interesting property. This satisfies what? Let me write. For any real x1 and x2, by the way, this is a Cartesian product. So what does that mean? This is a set. And this is a very simple Borel set in this two-dimensional Borel sigma field. Okay. And this one is nothing but your friendly joint CDF of x1 and x2 evaluated at x1, x2. So what does that mean? As far as two-dimensional random vector is concerned, this sample space and event space are common for all 2D random variables. You just need to specify the induced probability measure, and which is equivalent to what? The 2D CDF. That's why 2D CDF is more fundamental than this rather heuristic 2D PDF. Got it? And if you want to relate the 2D PDF and 2D CDF, it's very simple. You have two-dimensional integration of the two-dimensional density of x1 and x2. Let me use xi1 and xi2, d xi2, d xi1. Of course, my handwriting of xi is very sloppy. I still can't improve my handwriting about lowercase xi. Okay, but anyway, please read it as xi. Okay, so here your variables are x1 and x2, and these appears in the upper limit of the 2D integration of your joint density of x1 and x2. Got it? So if I plot, then what happens? This is xi1 axis and this is xi2 axis, and you have some point x1 and x2, and you have this entire quarter plane to integrate your density. So here you have some two-dimensional density or 2D histogram normalized, and then you integrate that area to assign it as this probability. Got it? And about the more relation between the 2D CDF and 2D PDF, and if 2D random vector is discrete, 2D PMF can be found in the note. For example, let me show you, okay, this would be interesting. Here goes some very short code, MATLAB code, that gives you this kind of 2D histogram. Histogram 2 is the official command of the MATLAB. Got it? So you just try something similar. And there are even homeworks, okay? And even solutions. And I have given some other things. Joint CDF and its properties is simple extension of what you've done for the one-dimensional case. Here goes the case where the random vector is discrete, and you have something interesting like this. Okay, CDF looks like this. CDF is monotone increasing towards the plus infinity comma plus infinity, something like that. And here was the properties of the CDF when you have two random variables, x and y. That's simple extension again. And here goes the marginal CDF, which is very important topic. So let me go back to our top page. Okay. And where are we? Yeah. Here, we need to talk more about that. So what is the margin, by the way? So when I was first taught about this marginal PDF or CDF or PMF, I just considered some economics related meaning of margin. So it was very confusing. And eventually I searched in Google and found something like this. So suppose you have a book, especially for accounting, in Korean 회계 장부, especially if you have I don't know, double accountant, 복식부기, you have some tables anyway. So what you do is that you write the item, and here is the price, something like that, right? And then another one. And eventually you have something similar to Microsoft Excel. And what you do is that at the margin, so this is the margin of the paper, right? When you set up the page before printing, you set margins, right? In your A4 paper. In the margin, what they write is that sum of all the terms, sum of all these terms, sum of this one, sum of that one, and compare, right? Actually, that is what I did when I was a military accountant. I said that, actually, assistant to accountant, because I was in Korean 육군 격리 행정병 when I served in the military. Okay. And my wife says that she can count better than me, and I despise. I have 1.5 year experience. Anyway, so marginalization is not related to each cell in Excel. It's related to sum, right? Right? So in the margin, you have sum already summed up. So now think about two-dimensional case, and suppose each cell represents the density. Then what about these values in the margin? What about these values in the margin? You can easily see that they are related to what? Given x1 and x2, they are related to density of x1 and density of x2. So the question is that find one-dimensional densities from two-dimensional density. And the procedure to obtain this single-dimensional density is marginalization. Got it? Because you can get the margin, something written in the margin. Got it? But it's not easy in the first glance. And approach is what? We use CDF. So whenever you have difficulty, try to use CDF. Never think about, rarely think about the induced probability measure. Got it? Because that is anyway equivalent to the CDF. So whenever you have something difficult, try to use 2D CDF. So here goes the question. So instead of finding the marginal distribution, PDF of x1, think about marginal CDF. What is this? This is simply probability of event that x1 is less than or equal to x1. Now, the trick is that you replace the event using equivalent event. Now you want to use the joint density of x1, x2. So what you do is that something like this. Sorry. Of course, that comma means end. Okay. Are they the same? Right? x2 can be anything, and it doesn't matter, right? The union of these two events. Because this is just what? Translated to the entire sample space of the underlying probability measure. This union doesn't matter anyway, right? So the trick is that you replace this event in terms of x1 into this equivalent event in terms of x1 and x2. Then you can use the definition of joint CDF. How? You find that here goes some trick that equals probability of event that x1 less than or equal to x1 and capital X2 less than or equal to infinity equals f x1, x2, x1, comma, infinity. By the way, whenever you confront infinity as an engineer, if you are a mathematician, it could be different, but this should be understood as some number very large, some finite number, and then you take the limit. The problem is that I have equality here. What does that mean? So I'm saying that if you just claim that's all correct, you have to be careful to check whether there is a point mass at infinity or not. Okay? If there is a point mass at infinity, this could be okay. If you have point mass at infinity, but you regard this as a finite large number and you take the limit, you are in danger. Because even though you take the limit, you will never reach infinity, right? So be careful. But anyway, so this is the idea. As far as the situation is understood, this infinity is understood as you really evaluate, you really include all the probability mass, even at infinity, then this marginal CDF can be obtained from this joint CDF. Now, our final question, how can you get the PDF? For the left-hand side, you just apply derivative. You differentiate this CDF. But what about this one? You differentiate with respect to x1 when it is already evaluated. So what you do is that you replace this one first with the integration in terms of the joint density. So the trick is this one. According to our definition, this is simply x1 joint density xi1, xi2, dxi2, dxi1, right? And you have here the CDF. Now let's differentiate with respect to x1. Then left-hand side becomes the marginal PDF of x1. And what about the right-hand side? You've already learned, according to the Leibniz rule, if you don't have something strange, you can just remove this integration and this dxi1 to get the result. So what you have is you integrate over x1, x2, and be careful, this must appear here, xi2, dxi2. Got it? So the right-hand side is still a function of x1. And this idea is very similar to what I have drawn here on the left upper corner. You have a page of an Excel sheet or an Excel sheet, and this row represents x1 values, and this column, each column represents different x2, and now you want to obtain the margin here. Then it's the function of x1. How can you get that? You sum up. And let's take a look at this one. You have an Excel sheet, and at each row, you sum up all x2. Exactly that idea, okay? So probably you just memorize that result when you're an undergraduate student. Now you have a better idea, okay? So always try to visualize something, and you can expand your idea. You never forget that idea because now you fully understood. Got it? Okay, anyway, so there are many marginalizations. Sometimes, suppose you have 100 random variables. 10 random variables. Marginalization does not mean that you get the individual random variables, single, one-dimensional something. Sometimes you marginalize so that you only have 5 random variables. That is also marginalization. Got it? So never too much stick to the 2-dimensional case. Anyway, now our topic moves to the conditional CDF, PMF, PDF when we have 2 random variables. And since I've run out of the space already, I'm going to move to the corresponding pages in the lecture note. Okay. So I've covered a lot actually, and you have to read that. Okay, I've done this part already. By the way, from the 2-dimensional CDF, by twice differentiating that, you can get the joint PDF. And you've already learned that, so I'm not going to talk about that. There are many different ways. So that, see that here, they use the y instead of J1, J2. But anyway, here, what is important is that you have the right-hand side, x left as a function, functional parameter. And you have x. Okay, what else? Marginal density. Okay, yeah, k-dimensional marginal PDF, right? Something like that. You have more than k random variables, but you only choose n minus k variables to integrate, something like that. Okay. Now here goes the conditional CDF, PDF, which is one of the most important topic. Okay. So this is the review part. Suppose you have a single random variable x, and you wanted to extend your idea of conditional probability measure involving the notion of random variable. What did you do then? So at that time, the idea is that you choose some event B and then considered something like this. So conditioned on the event that X is in the set B, what is the CDF of X? So it's like you have unconditional CDF of X, and now you have a conditional or the posterior, or in Latin, a posteriori CDF. Okay? By the way, italicized a posteriori is equivalent to the posterior in English. Got it? So 사후, this entire thing means it's an adjective. Okay, 사후 CDF, PDF, probability, something like that. Okay, anyway, in order to find that, we just use the idea that CDF is nothing but probability. So this is simply probability of event x less than or equal to lowercase x given the event. And now we use our chapter 1 idea. So given this probability of x in B, we compute the intersection joint probability of 2 events. And if we want to find the corresponding conditional PDF, we just differentiate with respect to x. That was the idea. Sometimes this event was a point condition, right? As I've already told you, x is Gaussian 0, 1, but you have an event like this, x equals a, and I'm asking you, what is this one? And that is, as your intuition says, see that? It's like this. This can be understood in two ways when you generate the scatter plot. What you do is that, as I emphasized, that you should be able to use the indicator function. It's like this. You generate and you check whether the realization satisfies that condition, x equals a, or some event b. If it satisfies, then you put a dot in your scatter plot. Otherwise, you drop it. That is the idea of generating conditional scatter plot. Got it? And then you have conditional histogram. And then you have conditional PDF. And you have conditional CDF PMF. Got it? So in this case, consider a small bin. And of course, if you choose point mass in a continuous random variable, its probability is 0, but you can always have some margin, right? Or some space, maneuverable space. And then if your output of the Gaussian random number generator is close to A, you say that, okay, it's close enough, and you put a dot, right? If it is far from A, you just drop. And eventually, you will observe only points located at A. Then what would be the histogram? Something like this. What is the limit of that delta function? So that is the idea, okay? That is the idea. So it's kind of, you have an indicator function multiplied to that. And you can find that actually approach already written in the previous chapter's note. Anyway, so now here goes the difference. Suppose you have two random variables, x and y. And now you know what I mean. Here is a random experiment that generates sample S, and it's copied and fed to two measurable functions named x and y. So now you have a random vector. And here goes the idea. Find the conditional PDF of x given the event y equals y. And here I still remember, I'm not kind of despising the educational level of Tsinghua University located in Beijing. But when I was a professor at University of Massachusetts at Amherst, there was a graduate student who got the undergraduate degree from Tsinghua University. And when I talked about that, he said that if y is a continuous random variable, that event has probability 0. So I can't consider the conditional point condition. So I said that, no, that's not true. Okay, you have to consider some margin, blah, blah, blah. Anyway, he didn't like my explanation. Probably at that time, my English was much poorer than now. But anyway, and after finishing his later, by the way, before he graduated, I left the University of Massachusetts and joined postdoc. And later I got to know that after he got the master's degree, he moved to MIT and got the PhD degree. Okay, so if you couldn't fully understood the meaning, and if you couldn't clearly 100% sure about that idea when you are an undergraduate student, it's okay. You are level of Tsinghua graduate. Got it? Anyway, so you have two random variables fed by a single S. By the way, when you have two random variables, there are two cases. I have to talk about that. So here, single random experiment generating outcome, and you have two functions, right? We are considering this case, but sometimes we have two separate underlying experiments governing two random variables, right? This is totally okay. The problem is that we do not know how to fully characterize these two things, because we didn't say that these two possibly sub-experiments, how they combine to a single experiment, right? As you've seen in Monty-Hall problem, there are around 3 or 4 sub-experiments, if you name it. First, host hides the BMW in one of the doors. Guest chooses one of the doors. Host, depending on the realization of the first event and second event, first outcome and second outcome, he chooses which door to open and show. And the fourth one, actually, that's not important in the computation, but anyway, the guest that decides to switch or stay, right? So you have 4 sub-experiments, and they are dependent. However, if you just say this, we don't know how they are combined, how they should be combined. In that case, this x and y, although they are random variables, are not said that jointly distributed. So in this case, not possibly yet jointly random or jointly distributed random variables. But in this case, x and y are jointly distributed, or jointly random variables. Okay, so jointly means that they have single underlying probability space. Got it? So jointly is very important. Anyway, so we are given 2 jointly distributed random variables, x and y. So we have this case. And my question is, what is the conditional PDF of x given y? By the way, here goes the notation I skipped. As we have written in this way for the single random variable, joint density is written this way. See that in your subscript, you list the random variables with comma, because if you skip this, it's hard to distinguish whether it's a density function of the product of x and y or joint density of x and y. So that's why we put comma. However, in many textbooks, when the context provides you whether it is a product distribution or joint distributions, many people just skip putting commas. Be careful, okay? And these arguments are separated by commas. And the first one corresponds to the first random variable. Second argument corresponds to the second random variable. Got it? But sometimes, what if you have 2 random variables marked by x1 and x2? Then sometimes people use f subscript random vector x evaluated at 2-dimensional point x. Okay, so this is also a very succinct or very shorthand notation. Got it? Random vectors density evaluated at some point. Meaning is the same as this one. Got it? Now, this is for the unconditionals. Now, what about the conditional density? So this one, the conditional PDF of x. So it's a density of x, right? So you want to say this one. And given y. So here comes the first notation. What about this one? Does it look good? Right? If you read from left to right, it exactly says that the probability density function of random variable x given the event capital Y equals y. So it's totally legitimate. It's okay. It's good. However, due to some certain reason, you will see in the chain rule or other thing, people love to use, I'm not saying that this is the only way, love to use something like this. Be careful. Anyway, this function has two arguments, right? As we've seen here, two arguments, x and y, right? So according to our ordinary math notation, this conditioning bar looks weird, right? We just put comma here. However, people love this notation, and that is one of the source of confusion. However, you have to admit that. Anyway, that looks very useful later in talking about handling the conditional probabilities. Anyway, time's up, so let me stop here and continue on this Thursday. I'm a little bit frustrated that we are still in this section 4.4. Okay, I hope we can finish this chapter 4 this week. Okay, that's all for today.